Way back in the summer of 2021, I came up with an idea, and I could not stop laughing. On a given trip, how many times do your turn signals flash? This is the story of unnecessary discrete logic, the sunk cost fallacy, and insert BMW joke here. The same day I came up with the idea, I decided to hack something together with an Arduino, as I simply wanted to see this experiment take form. Quality of form be damned. I essentially probed the taillight with a few wires, power and ground from taillights, and a wire coming from each turn signal.
You know, here I am, counting turn signals.
At the time, I had a 180-mile drive ahead of me, and the plan was to do the entire drive with it counting. However, after a brief test drive, I wasn't feeling it now, Mr. Krabs.
Alright, I just drove like 1.8 miles with this on. And while, yeah, it fucking works. Oh my god, that was terrifying.
It all didn't feel right, and at the time I was about to give the car up to my brother soon anyways. With little opportunities, a lack of time, and the used car market at the time, I decided to shelf the project. Eventually in November, I found a vehicle and time, and now it could be done properly. That is to say, we don't need microcontrollers where we're going, just our little friend, the SN74 LV8154 dual 16-bit counter, displaying to sub 7-segment displays. This little chip is exactly what it sounds like. Two counters that count up in binary, from 0 to 2 to the 16th minus 1. The two counters can run independently of each other, i.e. one counter for the left turn signal and one for the right turn signal, although they can be daisy-chained together for a 32-bit counter, much like how I daisy-chain the standard 4-bit counters in my clock and music box.
Look at my other videos, please. This is a plug. Check.
Anyways, from there, these 7-segment displays can be used to display the numbers. This is done with 7 LEDs, each of which have a common anode. Certain combinations of them can be lit up to display one hexadecimal digit, that is 0 through F, or 0 through 15 in decimal. Or they could also just say anything you want. These 16 digits can correspond to 4 binary bits, which means I have 8 of them, or 4 for each counter. So in summary, this will essentially boil down to the dual counters each sending 4 bits to each display, with some sort of logic to convert between the binary numbers and the 7-segment display patterns. However, doing it all in parallel like this is very impractical, as this requires 57 pins on the displays, one for each LED in the common anode, 32 output pins on the counter IC in addition to power, ground, increment, and control stuff, 8 identical clones of the converter circuit. This is not cool and good. But you know what is? Imagine, if you will, a system with numerous inputs from various sources, each to be processed and sent to their own outputs in the same way. These can be run in parallel, with one processing stage between each input and output. However, this means you need to clone the processing stage a bunch of times. This is stupid and redundant. Thus brings us to time domain multiplexing, which takes all inputs and lets only one of them pass through to the processing stage. After the processing stage, we can select which output it must go through. Essentially, we can cycle them through each input/output pair to let all of them come through. If every output needs to be continuously updated, then just do it really fast. It's one of the fundamental rules of electrical engineering. If you flicker something fast enough, it is not flickering. Both the counter and the displays are actually designed with this sort of multiplexing in mind, as it means less pins on the package. On these quad displays, the cathodes of each respective segment are tied together, which every anode on a single display tied together. What this effectively means is that by using the cathodes, you can select which segments to light up, and with the anodes, you can select which display to use. As such, you can use time domain multiplexing to display multiple different numbers. Basically anything that uses a 7-segment display does this. It's cool to look at in slow motion, but it can be annoying to photograph depending on your camera's shutter speed. In order to properly multiplex, we need to have a sort of system that cycles through all 8 anodes one at a time. This is done primarily with 3 blocks. A 3-bit counter that counts up from 0 to 7 in binary, a decoder that converts this to a 1-hot notation, and a good old 555 timer to provide a clock signal that constantly counts up. As for the counter, it has a single 8-bit output bus, and there are 4 pins to display which set of 8 bits goes to the output bus. Counter A upper byte, counter A lower byte, counter B upper byte, and counter B lower byte. This output bus actually has the bits for 2 displays, which can be addressed by multiplexing the counter at exactly half the speed at which the displays are. This is done using OR gates on the decoder outputs. Splitting the bus in 2 is not necessarily an issue, as it can be easily addressed with the goal of the processing stage is to A. Convert binary numbers into 7-segment display patterns, and B. Have a way to select the upper half or the lower half of the counter output bus. This largely amounts to a giant block of combinational logic, which essentially means that its output is dependent on the current state of the inputs and nothing else. The first step to designing the circuit is to draw a truth table, and what follows is in fact not Boolean algebra. Just change some labels, and maybe do a bit of rewriting, and now it looks like some data which can be written to an electrically erasable programmable read-only memory, or EEPROM for short. If the address and data buses are both parallel, it can essentially act as a lookup table for any truth table we come up with. After programming the EEPROM, we have a display. Now all that remains is... Oh hey, remember how this was about turn signals? So yeah, now we just power this from the cigarette lighter, probe the taillights, and play the travel montage. Seems as if I forgot to answer the question that led me to build this device. How many times do your turn signals flash?
676
On the left,
and 360
on the right, over a 145-mile trip.
Break.